Hi there. In this video, we're going to explore the empirical rule and how standard deviation ties into this. The empirical rule is also known as the 68, 95, 99.7 rule. And the reason for that is that refers to the probability associated with 1, 2, and 3 standard deviations away from the mean. Now, for explaining the empirical rule, I'm going to give you two examples here. I want you to think about, let's say, test averages for a class. So let's say that in Rachel's class, on test 1 for the semester, so let's say the first unit test, my students had a mean score, so I looked at the whole class, so a population score here, a mean score of 82 with a standard deviation of 9.5. So that means mean of 82, standard deviation of 9.5 points on the test. And then on their, let's say, unit 2 test, they had a mean score of 98 with a standard deviation of 15.7. Now, we can already start formulating some ideas about what those means and standard deviations might mean if we're familiar with coefficient of variation and we're trying to look at how consistent the data are. But we can also use the empirical rule to learn about the differences between these distributions. And in this case, I'm going to go ahead and pull up these two blank normal bell curves. So anytime you're dealing with the empirical rule, you're always going to start by placing your mean in the center. So for the first, I'm going to go ahead and color coordinate these actually. So I'll use blue for the first unit and green for the second unit. So the one on top will be the unit 1 test. So I have a mean here of 82. So I'm putting that dead center here. Now, a standard deviation, to go one above, I would add that 9.5 to my 82, or to go one below, I would subtract it. So how do you go and calculate those values? Well, what you're going to do here is start with your 82, and let's go ahead and find the above values first. So I have plus 9.5, so that means that this first one would be 91.5. Then to get two standard deviations above the mean, I would add another 9.5 to that. And you'll notice that brings us to 101. And then same thing again, to get the third standard deviation above the mean, you would add another 9.5. Now, for sake of illustration, let's just go with the points that are here. If we're talking about tests, don't worry about this going over 100%, but that itself could tell you something about the data in this distribution. That's for another video. Now let's go ahead and fill in the values below the mean. So -1 standard deviation, -2, -3. For that, start out with your mean and then subtract 9.5 from each one. So one standard deviation below the mean would be 72.5. And then rinse and repeat that process. So once again, subtract, we get 63, and subtract one more time here, and we get 53.5. We'll revisit that Unit 2 test in a few minutes. For now, let's talk about what we have learned so far and how the empirical rule applies here. So what the empirical rule states is that based on 1, 2, and 3 standard deviations respectively away from the mean, it contains 68% of the data, 95% of the data, and 99.7% of the data. So in other words, if we're looking at this, the mean in the center, to the left of that, so if this is the mean, then to the left is the mean minus 1 standard deviation. That's how we got that number. To the right would be the mean plus 1 standard deviation. So what this is representing is that from this line to this line, so that's from -1 to +1 standard deviation, drawing those lines on our normal curve, this area, from here you can imagine these lines go up further, but this is 68%. So in other words, 68% of the class scored between a 72.5 and a 91.5 on the Unit 1 test. And similarly, from -2 standard deviations to +2 standard deviations, we would say 95% of the class met that mark. So let's look at what that would be. So from -2, that's 63, up to +2 is 101. That's 95% of the class. So basically at this point, almost the entire class is between a 63 and a 101. And last but not least, between -3 and +3 standard deviations, that would be your 99.7% of the class. So this time, definitely almost all of the class scored between those two values. And of course, you can make some inference from this. I look at that and say, well, some people did fail. Almost the entire class did complete the test at least at a 53.5, right? So it really varies what kind of observations you can still make from this, but in terms of understanding the empirical rule, you should just know that it's specifically looking at anything from -3 standard deviations all the way up to +3 standard deviations. Now, the reason I put the second example here, and I think it's interesting for us to look at, is if we take a look at that Unit 2 test, it allows us to compare kind of in the same way, right? So these are standard deviations are a standardized score representing the distance away from the mean. So if we look at, again, our mean in the center, actually, you know what, let's go ahead and change these numbers just so they're a little, maybe let's make this 95 and we'll do just a standard deviation of 1 to keep the numbers a little simpler for now. So if we put that mean in the center of 95, well, -1 would be 95 minus 1 is 94. -1 again is 93, just because I specified a standard deviation of 1. -1 a third time is 92. And then you're going to fill in the other side as well. So this would do +1. So 96 plus 1, 97 plus 1, 98. Now, if you look at the Unit 1 test versus the Unit 2 tests, the percentages are the same. But what's different is the boundaries between them. So here, if we have our mean in the center, and then we go from -1 to +1 standard deviation, we can say that 68% of the class scored between a 94 and a 96. That was very different than the Unit 1 test, where it was only a 72.5 to a 91.5. 95% between 93 and 97. And then last but not least, between 92 and 98, this represents 99.7% of the class. So if I were to see something like this, I would infer that the Unit 2 material, the students had to have stronger mastery on than with the Unit 1 material. If we're talking about the same group of students, just being able to compare how they did on the first test to the second test. Empirical rule does also go hand in hand with z-scores. So let's go ahead and create a separate slide here to talk about z-scores for a moment. So z-scores, to calculate them, you would always take your data value, x, minus your mean, divided by your standard deviation. Now, actually calculating these isn't so much what I'm concerned with right now, but talking about how this relates to the empirical rule is really helpful. So let's go ahead and I'm going to pull over the visual that we used on the previous slide just for the second example. So hang tight a second, pausing the video here. Okay, so now that we've got this image over, let's talk about what's going on here and how z-scores tie into all of this. So when we talked about your values being -1 standard deviation away, -2, -3, those would correspond to z-scores with 0 in the center, -1 is 1 below, -2 is 2 below, -3 is 3 below. And then on the right side, you would have +1, +2, and +3. You get into this usually much later after learning about the empirical rule, but it is important to note now that z-scores do correspond to how many standard deviations away something is. So just because we have this formula, you have to remember that a z-score is still the number of standard deviations away from a mean that something is. So for example, if I said to you, here, let's see, we had in this case, the mean was 95 and the standard deviation was 1. So what if I asked you, what would the z-score be if a student scored a 97.2% on their test? So 97.2, visually, if we're looking, so these are our percent score on the test, right? So 97.2 is probably somewhere over here. So we can see it's not quite a z-score of 2, but it's definitely not a z-score of 3. If you wanted that exact number for z-score, you can plug it into your formula. Z equals our data value x, so 97.2, minus the mean of 95. Divide that by your standard deviation. So what does this give us here? 97.2 minus 95 is 2.2, divided by 1 is still 2.2. So this has a z-score of 2.2, which if 2 is here, it makes sense that this would be just a wee bit further along. Thanks for watching.